today. But first, we're going to start with a little exercise, and this I'll need your participation in. So each of you actually has, is in your Zoom window, the option to annotate your screen. And when you do that, you can grab a little draw circle and put a little dot on the screen. If you do that, when you pull down your annotations, you'll see that there's a draw module over here. You can select maybe this little circle, and you can also select a different color, and then you can also mark the screen. So what I'd like for you to do is to grab your annotations toolbar and to mark on your screen, reflective of what we will all see, your birth date, month, and the first letter of your last name. All right, so we're seeing results coming in. It looks like the annotations function is working for everyone. It's great to see. If you had trouble with getting a specific symbol, you can try to use that circle if you would, and try to keep it fairly small, because we're going to do a little exercise where we're all going to share and try to predict something on the screen next. So it looks like it's working. Good. Well, let's move on then. So keep your screens up, and thank you. And so this is what our little our world of birthdays and names looks like. Interesting, kind of, that we see some patterns here, unintended. Certainly some months that don't really have anything, different colors that we randomly chose. So I'm going to clear everyone's drawing, okay? And I want you to get your circle again and choose whatever color you like. And I want you to do a simple exercise for me. I want you to draw a circle at the very center of your screen, exact center if you can. Something that is as close to the center horizontally and vertically as possible. All right, keep going. Looks like we're getting a pattern building up here. So what I'm asking you to do is make a prediction without really giving you a tool to provide any sort of resolution to your estimate, that you actually don't have a grid and you don't have a mouse that shows exact coordinates, and you're just estimating, okay? And the idea, of course, is that all of our Zoom screens have a rectangular but different rectangle shape. And Zoom is actually automatically scaling or transforming everyone's X and Y to common geometry, so that your center of your screen should be equal to the center of my screen if that algorithm is working right. So let's take a look at how our estimates fare. Okay, so this target represents the exact middle of your screen. of your black Zoom screen, top and bottom, side to side, centered. And of course, we actually did quite well in our prediction of the center. This was reasonable, and of course, we can see that there's some variation in that prediction. Well, how might we measure that variation? Well, if we had an exact knowledge of the true center, we would compute distances between each measurement, right? And we would sum that up, and that would effectively be variation, right? So we can imagine doing that, and we can certainly see that there's a general cluster here. We might have seen clusters in other places, but reasonably correct. Okay, so let me go back. So here we are. I'm going to carry on, and I'm going to erase our screens again. I'm going to ask you to repeat that exercise one more time. Find the exact center of the screen. Use your draw, little circle or symbol, and so with repetition and a little experience, we can see that our cluster tightened. Our variance now is smaller, and we can expect that maybe we're a little more accurate now. And in fact, we are. We as a group collectively can reasonably find the center of the page. Okay, and but if you wouldn't mind undoing that one, that'd be fine. Thank you. And so if we were to actually come up with our estimate of the true mean, we would see that, of course, it is somewhere in the middle of this cluster. I'm going to use a bright green because I don't see that one. The center might actually be right here, but our average is right about there, being pulled over by this little guy right here. And so we intuitively have this idea that there is a true middle, but we don't actually know what it is. We still don't really have it labeled. And so we have to use our best estimate of the true middle being our measured data, our actual observations as the estimate of the center. But what if our algorithm wasn't working right? What if Zoom had a bug that someone decided to code into it, hack into Zoom, and change that scaling algorithm so that as we're transmitting across all these different PCs, that maybe the horizontal measure is skewed a bit left. So if we had an error or if Zoom had an error in its calibration process, this in fact might be what we would see. We all measured the center right about here, but Zoom says the true mean is over here, and we see that there's some systematic offset. Actually, these might be the true values, and if we were to all have had an error, they would have all clustered into this middle. This offset represents systematic error versus the small variation and random error that we see in our predictions. So that's a helpful exercise, I hope, at explaining some fundamental concepts in error analysis visually. So here we go. I'm just going to clear all these out. This diagram does a good job of summarizing that as a dartboard. And over here on the left, we all have the same measurements, repeatable, no random error, but the accuracy relative to the true mean is off, or the true center. Here we have all measurements that are all right on target and right in the middle. And then here we have a spread of measurements, systematic and random errors, leading to poor accuracy. And that's sort of the big visual snapshot of what we're trying to sort of quantify when we do analysis, uncertainty analysis, is what is that level of error, what is that level of uncertainty, and doing that as precisely as possible or as repeatably as possible. So in experimental methods, our main objective when we're taking a measurement is to estimate the true value, x prime, based on information derived from repeated measurements of a variable, right? And so here's our repeated randoms. We see a difference in the center of the random as random error, reflective of a probability density function, often assumed to be normal or Gaussian. But then there is systematic error, where our true value is different from our average of our random observations. So that random error manifests in that scatter, but systematic error is the portion of error that remains constant when we take repeated measurements of the same variable, often reflective of an offset of the indicated value from the observed value. Okay, so let's carry that on into like a numerical estimate of what we're talking about there. Again, our true mean, we're trying to estimate our true value with a most probable estimate, usually our mean, plus or minus some uncertainty with an appropriate probability level that's associated with this statement. And so uncertainties then are the numbers that quantify the possible range of effects. And generally, even though we ignored systematic errors in Chapter 4, are reflective of both random and systematic errors. In looking at the random error component, we used sampling as a tool, and we came up with this student's t distribution as a slight correction for a finite sample compared to a population, and used that t from a t-table and also standard error to help us develop a precision interval. And then we used the standard error and looked up t-value to define a confidence interval, as we have shown here, representing that uncertainty in the mean value at p% confidence due to variation in the measured data. So we need to tie that random error concept and stats concepts back into full uncertainty, including systematic error, and develop a method to do that. So here's the 10 keys for understanding uncertainty. First, uncertainty analysis itself provides a methodical approach to estimating the quality of the result of a test. Estimating the quality of a test. How good is that test? Okay. How good is the result of that test? It's always the plus or minus something, plus or minus what if, this red guy right here. That's what we're always talking about with uncertainty. But we have to be careful in our terminology. Error is a property of a measurement, and uncertainty is a property of a result. Error is a property of measurement, uncertainty a property of a result. Errors are effects, and uncertainties are numbers. Okay, so if we knew an exact error, we actually could just correct for it. That's important to know, like the scale that we might zero out. But of course, we're talking about measurements, which is the process of assigning a value to a physical variable, and the outcome being in and of itself a result, but one that we almost always only know the sample of and don't know the population or the true value of. Errors cause differences between assigned values and true, and we usually don't know that true value